Thank you so much, Tom, for the invitation here to hold the keynote talk. It's a great honor to be here. I sort of have become a bit of the face of OpenCL on the internet with my project. I want to give you a bit of an update what I've been working on with FluidX3D over the past years. So my formal background is in physics. I have a PhD in physics from the University of Bayreuth, but I'm really burning for computer science and high performance computing and GPU programming. So I've been working on FluidX3D for the past 7 years, and then about 2 years ago joined Intel, and it puts me in an interesting position because I'm an independent software vendor of FluidX3D, but also at Intel, and have a lot of connections there. So my talk today is about scaling up FluidX3D beyond 100 billion grid cells. That is a gigantic amount of resolution on a single computer, which means that the energy consumption is a lot smaller than what you usually would need for these kinds of resolutions. And that is a very nice story about the true cross-compatibility of the OpenCL language. Yeah. So what is FluidX3D? I put here the GitHub page as the first thing. So it's github.com/projectphysics/FluidX3D. It is the most memory efficient and fastest lattice Boltzmann computational fluid dynamics software out there. And I wrote it from the necessity to have such a software as a tool for my own PhD work, for my research on raindrop splashes like this here. There just was not such a thing, a software that could compute thousands of raindrop splashes at very high resolution in a reasonable runtime. So I had to do it myself. And eventually I decided to give it a rewrite and put it out on the internet for other researchers and hobbyists and maybe even teachers to use and explore the code and learn from it. Most of it is written in C++, about 2/3, and about 1/3 is OpenCL. That is around 3,000 lines of OpenCL, and in total it's close to 10,000, so it's a very compact code with minimal dependencies on external libraries. So the entire rendering engine, I wrote it all myself, that helps with the cross-compatibility. The popularity of it has really shot through the roof. This is a chart of the GitHub stargazers over the years compared to some other fantastic open source codes like OpenFOAM and SU2. And with over 4,000 stars, there's a lot of users out there. The rankings on the GitHub topics, I'm #1 in CFD, which is crazy, and #6 in HPC, and 9 in OpenCL. So part 1 OpenCL. 7 years ago, when I started with FluidX3D, it was one of the best decisions of my life to go with OpenCL and not CUDA. OpenCL has gigantic advantages. It is out of the box compatible with like all hardware, all GPUs from all vendors. That includes AMD, Intel, NVIDIA, ARM, Apple, even some exotic vendors like Glenfly, who you probably never heard of. And all gaming, workstation, data center, and even the integrated GPUs. It also runs on all modern CPUs, AMD, Intel, and even Xeon Phi. And with modern, I mean like CPUs manufactured in the last 20 years, basically. they all run either the Intel CPU runtime or Pocket. And it also runs on FPGAs and accelerators. The performance, if you really optimize it, is identical to CUDA. There's no drawback in performance. The great thing is you only need to optimize your code once, and then it is optimized across almost all GPUs. Of course, there's some like differences when it comes to very special instructions, but general optimization techniques are the same. And you don't have to port the code anywhere because it's just out of the box compatible. To showcase the compatibility, this is the performance chart of FluidX3D across different hardware. So here, this is most of the GPUs that you're probably familiar with, all of the NVIDIA gaming GPUs, entire RTX lineup, so Ada Lovelace, Ampere, Turing, this is the GeForce 10 series, and it's a lot of GPUs. Then there's the Intel GPUs, the ARC A770 and the new B580. Also all of the AMD GPUs. So this is all of the consumer GPUs. What they have in common, why I can classify them as or like put them in a group of consumer class GPUs, is that they all have quite poor FP64 performance. Then there's a class of data center GPUs, and they have quite high FP64 performance. That's why I still group them together. With FluidX3D, it doesn't really matter because it's only using FP32 floating point. But here, this is all of the expensive GPUs, NVIDIA Hopper, the Intel GPU Max, and AMD's GPU lineup. And what's interesting is AMD, they have done the hockey stick. So performance was reasonable for the last generations, and then MI300X is a bit off the charts. Yeah, and then FluidX3D also runs on integrated GPUs, and there's very exciting options also here. There is the Intel Meteor Lake, for example, where you can just plug in 128 gigabytes of memory. AMD's integrated GPUs, there's also a new one, Strix Halo, but it's not yet on this chart, unfortunately. And this is the Apple integrated GPUs from the M1 and M2 chips. They have quite good performance. And if you need more memory, you can always go to CPUs. Most of them have quite low performance, but there's exciting developments on the server CPUs with Xeon 6. I will come to that later. So it runs on all of this hardware. It doesn't matter what hardware people have. They can just deploy it and run it. Yeah, let's go through the Lattice-Boltzmann method. So FluidX3D under the hood is a Lattice-Boltzmann code from the mathematical side. It's the most simple Lattice-Boltzmann variant there is. So this is the entire algorithm for it. Consists of two steps, a screening and a collision step. And the first thing to introduce is Lattice-Boltzmann consists of these so-called density distribution functions. And they're visualized here as these color bars on the grid. So each grid cell has in 2 dimensions 9 density distribution functions. One, that's a dot in the middle, and then left, right, top, bottom, and the diagonals. And you can imagine those as sort of groups of molecules that stream around on the grid. And so they move across the grid. When they're in one cell, they get collided, and then they can move again. It's a streaming collision. And in the software itself, they are floating point numbers. So the first part is the streaming, where they just move across the grid. In software, that means just copying numbers in memory. That's all it does. And then once they are streamed, the summation of it is the density row. So you just sum all of them up. That gives you the fluid density at the local point. And then you can also sum them up with directional weighting. So all the distribution functions pointing to the left minus all the distribution functions pointing to the right. That gets you the velocity in the x direction. And that's all you want to know from a CFD simulation, the velocity and the density of the fluid. From velocity and density, you compute the so-called equilibrium density distribution functions. And then you collide them, and that finishes the collision step, so you can go on to the next time step with the next streaming. The quantities marked here with the boxes is what you need to store in memory. So the density, velocity, of course, and also these distribution functions, they all need to reside in video memory. Additionally, you need some sort of flags which tell you if a grid cell is a solid or fluid grid cell, or some other boundary condition, or for the free surface extension, fluid interface, or gas cell. In 3 dimensions, there is various options how to discretize the grid. So 2D, we already know there's 9 of these distribution functions. In 3D, you have the options with either 15, 19, or even 27. And the one with 19 is the most common. It has still reasonable memory footprint, but is also very accurate already. So there you have the streaming directions to the sides, to the edge diagonals, but not to the space diagonals. Yeah, counting the bytes. In order to scale up a lattice Boltzmann, you really need to optimize it on the small scale on the single grid cell level. Lattice Boltzmann has a big problem, that's the memory footprint. So it runs exceptionally efficient on GPUs because all the grid cells, they can be computed independently from each other, but they all need quite a lot amount of memory because of all these density distribution functions. And the GPUs don't have a lot of memory, which is unfortunate. On the gaming cards, you get like 8 gigabytes or 12 or 24 gigabytes, but it's not too much. So it's fast, but the memory footprint is too high. Let's look at the memory footprint in detail. This is a single lattice Boltzmann grid cell, how it looks in memory. So you get 8 bytes for the density as a FP64 number, 24 bytes for 3 velocity components, X, Y, and Z, and also 64-bit integer for the blacks, and then all of the gray stuff is the density distribution functions. And you aren't even interested in those because all of the observable variables are the density and the velocity. And yeah, the footprint of this is 344 bytes per cell. It's horrendous. In 1 gigabyte, you can fit 3 million grid cells. People have already realized before my time that it is sufficient to go with FP32 precision. The reduction in accuracy is not even noticeable because the discretization on the grid brings a lot higher error than floating point arithmetic. And with that, you already are down to 169 bytes per grid cell, which means you can fit 6 million cells in 1 gigabyte. And what I did as part of my PhD was to compress it down to 55 bytes per grid cell, which means 19 million cells per 1 gigabyte of memory. And compared to the top one, that's a 6-fold reduction in memory, which is gigantic. Considering that, in one RTX 3090 GPU with 24 gigabytes, it can do the same like 450 million grid cells as in some other codes, you would need 2 H180 gigabyte GPUs. That is like a factor somewhere between 10 and 100 in hardware cost that you're saving with a little bit of byte counting, essentially. Now, how to get there? There is 2 steps to reduce this memory footprint from the FP32 baseline to what I have. The first is realizing that lattice Boltzmann on a GPU traditionally is quite bad because it needs 2 copies of the density distribution functions in memory, 2 redundant copies. It's a bit like implementing the game of life, where you need to read all of the neighbor cells and do the ruling for the center cell and then save the new center cell to solve for the dependencies of neighboring grid cells. And what I did is a solution that gets rid of the redundant copy. So traditionally, you would do the so-called one-step pull scheme that you already saw. So the density distribution functions from the neighboring cells, they get streamed inward and then collided and then stored to memory. The bad thing here is that the memory load and store places are different places in memory. So when you have 2 GPU threads next to each other working on the same pool of memory, they would have a race time condition. And it wouldn't work. So here you need 2 copies. In 2017, Geyer and Schönherr found a very ingenious solution already. They call it the esoteric twist because it is so hard to understand that they termed it esoteric. And they shifted the density distributions by half a grid cell in memory and then did an intricate streaming pattern. And the trick here is that the load and store positions are always the same for the even and the odd time steps respectively, so they can get away with 1 copy of the grid in memory. The difficult thing here is that the streaming directions are not the neighbor directions. In 2D, this is this population, they are not like down here, which makes implementation a bit of a pain. When I implemented this, I found sort of by accident that you can actually do that. You can shift the distribution functions that are not in the streaming directions into their appropriate place. And it works. And I call it then the esoteric pull scheme. There's also a push variant of it. And yeah, here it's a lot simpler to implement. It's like 15 lines of code. It still has only 1x memory demand. It only needs one copy of the grid, and it is the optimal pattern for coalesced memory access, because the one extra population that is in the streaming direction in 2D and in 3D it's a bit more, is also coalesced memory access. So part 2, from 93 bytes per cell to finally 55 bytes per cell. That is realizing that all of the numbers, except for the flags, are stored in FP32 and they take up 4 bytes each. So what if I could just compress them down into a 16-bit floating point, only the density distribution functions? And it wasn't as easy as it looks like. So the first idea was here to decouple the arithmetic position and the memory position. So all of the math is still happening in FP32, so we don't lose out position. In the memory storage, we can choose either FP32 or FP16 with compression. And in between, we have a conversion. With the standard lattice-Boltzmann algorithm, unfortunately, it doesn't work quite well, because when I look at the distribution of the density distribution functions of these, like where do the floating point numbers, where are they located on the number line, I find that they are centered around the lattice rate. So one is around 1/3, 1/18, and 1/36. And this is not good behavior if you want to have the highest precision. So there was a trick in 1993, before my time. someone found a solution that with a few very simple modifications to the lattice-Boltzmann algorithm that don't change any of the physics behind it, you can shift the density distribution functions so that they are all nicely centered around 0. Floating point numbers are most accurate if they are not spread all across the number plane, but are very confined close to 0. And the modifications here is just for the density, you add a 1, and for the equilibrium populations, basically you subtract the lattice weights, but you can modify it, shift it around a bit, so you get this additional term. Yeah, then let's explore possibilities of FP16. It is not as simple as just going with the IEEE 754 FP16 format, because that is not the optimal format here. I have visualized then here how they are stored in bytes. So floating point numbers, they are divided into 1 bit for the sign, a number of bits for the exponent, and an even larger number of bits for the mantissa. And I've visualized the amount of decimal digits you get here in this chart. So the precision you get with a floating point number is not the same everywhere. It depends on what the value of the number actually is. For FP32, it looks like the same precision everywhere, but if you go very far here to the left, it would somehow somewhere still make the slope. So this part where it's at constant precision is called the normalized range. And then it does the slope. This is the so-called denormalized range, where you shift the mantissa back, which costs you precision, but it lets you still you can still have very small numbers represented. The IEEE FP16 format is here the yellow line, so it goes from here to here and then up to here. And this is not optimal because the density distribution functions, as we know, they're very close to 0. We don't need the number 65,000 represented. So the first thing I tried was just take this and shift it to the left by just shifting the exponent by 2 to the power of -15. And that gets me the shifted FP16 IEEE format. I call it FP16S for simplicity. And then I explore some more. What happens if I steal one bit from the exponent and put it into the mantissa? That allows me to have higher precision. So that is here this purple line. It is a bit above in the amount of precision, but it is squeezed down. So you can't represent that large of a number range here towards smaller numbers. And then I also experimented with some posit formats, a very interesting alternative to floating point. If you had more than 16 bits, posits are far superior to floating point actually, but in this application with just 16 bits available, they are not so much better than floating point. How posits look like, it's interesting. That's the blue line here, they look like a pyramid. So with slopes on both sides, they have the highest precision in the middle, and then precision tails off to either side with different slopes. I even did an asymmetric posit format that has a very shallow slope only in one direction. But here we are only concerned about the shifted FP16 and the custom FP16 formats. They work both. They work best for lattice Boltzmann. So in the shifted format, you have more range towards tiny numbers, and in the custom format, you have halved truncation error. Let's look at the custom format. So the idea is steal one bit from exponent to make the mantissa larger, and then tune it to have the range of ±2, which is totally sufficient for lattice Boltzmann. You get 3.6 decimal digits instead of 3.3. The truncation error is cut in half, so it has superior accuracy, but the range towards smaller numbers is less. The disadvantage is you can't use hardware conversion. The IEEE format, literally every modern GPU can do the conversion in hardware, but with the custom format, I needed to do it myself, and this is my algorithm for it. It's become quite widespread because it's branchless. It just uses some bit shifting magic, and it covers both the normalized and the denormalized formats. There's some even tricks in here, like in one place I need to count the number of leading bits, and there's a trick to represent a number from floating point as uint and then convert it back to float, which gives you an implicit log2, which is faster than the OpenCL count leading zeros function, which supposedly exists in hardware but actually is emulated. So in terms of instructions in NVIDIA PTX, it's around 51 instructions back and forth, and it does correct rounding and both normals and denormals, and literally every hardware can run it. There's no arithmetic happening in the strange format, only the conversion, and the conversion algorithms, they are universally compatible. Here's some test. The 2D Kalman vortex street with the different formats between the FP64 and FP32, there's absolutely no difference. With the FP16 formats, so what is visualized here is the vorticity, that is a finite difference between the velocity in neighboring cells, and in a very overexposed range to show even tiny numbers of vorticity. And with FP32 arithmetic and FP16S storage, you see that there's some artifacting going on, because eventually differences in numbers cannot be represented anymore because you only have so many bits of the mantissa available. The FP16C format with the half truncation error mitigates most of the artifacts quite well. But they all are physically accurate. This is like after 50 vortex periods, and the vortices are all in the exact same place. It's just that there's a bit more numerical noise with the lower precision. This is visualized with a probe point in the center, how the velocity goes back and forth when each vortex passes, and around after around 50 vortices, the curves are almost exactly on top of each other. This is another test setup, the lid-driven cavity. You can imagine this like a truck with a open trailer, with a cubic box where the wind blows over it and it starts a big vortex in the trailer. And this is the velocity profile of it. So at the top, there's the velocity going around, and then the velocity profile here takes off a bit and gets shallower before it repeats. And with all the positions, the velocity profile looks identical, which tells me that the lower position works. Now to the interesting part, how to scale it up. One GPU is only so much memory, but multiple GPUs can get around it. So the idea is to do domain decomposition. You have a cuboid box and you split it up in the middle in 2 or even more domains. Each GPU only stores its own domain in its own VRAM, and it has no knowledge of the other domains. And in between, you need to share some data only across the boundaries. Keep attention for the periodic boundaries also. With Lattice-Boltzmann in 2D, with the 9 density distribution functions, at the edges, not all of them need to be transferred, but only the ones that are outward pointing. In 3D, this is only 3 distribution functions. In 2D, it's 3 distribution functions. In 3D, it's usually 5 distribution functions. Then, because of some extensions, you need an extra halo layer to copy the data into. So you give each domain 1 grid cell space on either side and copy this layer of grid cells into the halo and this layer here into the halo. How the copying works in a simplified manner is that at first from these big volumetric domains, you extract only the sites that need to be copied in transfer buffers. The domains, they can have tens of gigabytes. The transfer buffers are usually like 10 megabytes, so quite small. And this copy is happening in VRAM, so from VRAM to VRAM for each GPU independently. Then only the transfer buffers get copied over PCI Express into CPU memory to transfer buffers. Then the CPU can do a very cool thing. It can just swap the pointers, so it doesn't even have to do any in-memory copy. And after the pointers are swapped, they can copy back over PCI Express and copy the transfer buffer back into the big domain. So this is also called a system RAM hop. The advantages is that it is really cross-compatible. It doesn't matter if one GPU is AMD and the other is Intel. It works between any combination of GPUs. There's only single copies of the transfer buffers required. Other versions need duplicate transfer buffers. The disadvantage is that it only works on a single node. So as soon as the GPUs are spread across multiple servers, this out of the box doesn't work. There's ways around it. Jan is here with Pockle Remote. That is one way around it. And the other disadvantage is that it doesn't use GPU to GPU direct peer-to-peer memory copy, which is unfortunately not yet possible with OpenCL. In 3D, this is how it actually looks like. So each domain has transfer buffers, not only 1, but 2 on the left and the right of the box. So that's why we have 2 transfer buffers indicated with a plus and a minus. And they get copied at the same time from all domains. Then a double pointer swap is happening. And then this is repeated 3 times for the X boundaries, the Y boundaries, and the Z boundaries. And this works, so one GPU here can communicate with 6 other GPUs if it's really different GPUs. And the cells at the edges or on the corners, they are correctly handled because the data is really moved first to the neighboring sites and then from them up to the others. So it is fully functioning and it is binary identical compared to using a single GPU as long as all GPUs are the same architecture. So that's how I verified it. I use one GPU, run the simulation as a single domain, and then use the same GPU with multiple domains and check the results, and they are binary identical. Another trick that I'm using is that the device calls are all non-blocking. So I can tell all of the different GPUs one after the other enqueue this kernel, and it enqueues all of the kernel for all GPUs. And then I make another loop where I finish all of the queues, and this is a synchronization variant. So they all start at the same time and sync at the same time. And this means I do not need any OpenMP STD threads or parallel 4 implementation for it. I can just use the multiple device queues, which makes it simpler and even more efficient. There's another benefit with this single node architecture. You don't need a master copy. What I mean with that, with standard MPI, you usually have one master node and a lot of slave nodes. And the master needs a big copy of all of the slave domains for any sort of data dumping to the hard drive. And that like when all of the domains are huge in size already, you need gigantic amounts of memory on this one master domain. With a single node, I can make the master copy assembled on the fly for all of the domains. So for any grid index that is in this big master domain, I can just query which of the small domains is it and which position in the small domains, and then I get the data for it. So I don't need a big copy in memory. How to do graphics with multi-GPU, this is exciting. So each GPU only knows its own domain in memory. It has no knowledge of all of the other domains, so it can also only render its own domain. And it does so with a 3D offset. So it puts its own domain in its place relative to the others. And then I copy an image and the corresponding set buffer to the CPU on the CPU side. I do an overlay based on the set buffer for all pixels, and that gets the right pixels up to the front. And finally, the CPU sends the overlay image either to the screen or to the hard drive. I've illustrated this here. So this is 9 domains rendered all independently with a 3D offset, and each of those is accompanied with a set buffer. And when I overlay them on top, I get the final output image. You see there's some domains where you can see the inner parts of the plane, and of course there's other domains that are further in front, so the output image is still correct. Yeah, it is really, really cross-vendor. So I've recently demonstrated this on a Frankenstein server with different NVIDIA, AMD, and Intel GPUs. And it has 8 GPUs in there, and the A100 40 gigabytes, it's fast enough so that I can use one GPU to compute 2 domains, and then I have a P100, 2 A2s, Instinct MI50s, and an ARC A770 60 gigabyte GPUs. So each domain is around 15 gigabytes in size. And in total, 132 gigabytes with 2.5 billion grid cells. So this is the video rendered from it. The rendering works wherever the camera is located. So it works from all camera perspectives. And the runtime of this was like half a day. So a very reasonable, fast runtime. And because of the gigantic resolution, you get a lot of detail in the vorticity. The good thing about this cross-vendor multi-GPU, you might ask yourself, why would anyone have such a Frankenstein server? But not all people have an abundance of resources. And research groups, they might have some GPUs from an older generation and then some new GPUs added to that from maybe a different vendor even. And cross-vendor multi-GPU allows people to use the hardware they already have, so they don't need to buy anything extra. And when they really have to invest in new hardware, they can choose whatever vendor they want, whatever vendor has the best, in this case, memory capacity to price ratio. And the A770 was even leading it because it offers 16 gigabytes of VRAM and was the cheapest GPU to do so with still high memory bandwidth. So in the end, this has very high benefits for the end user of these applications. Yeah, multi-GPU. I did a demo last year also with 32 GPUs in a server that was a server from Giga.io with 2 terabytes of combined video memory, but that is also where it ends. So you can't have any larger GPU servers than 2 terabyte video memory still today. And if you have to go bigger, you need CPUs, big CPUs. And OpenCL also runs on CPUs. So that's what I was exploring next. Multi-terabyte memory CPU support. So the GPU VRAM capacity is limited. The highest end models, currently the MI300X, they have 192 gigabytes per GPU. In multi-GPU servers, you get up to 2 terabytes, but in CPU servers, you get up to 12 terabytes. And there's a very exciting progress happening at us at Intel, because last year we brought to market the Xeon 6 CPUs. They are gigantic. And the exciting thing is that they support MR-DIMMs. So MR-DIMMs are the very tall, double tall memory modules. They aren't real, they can't hurt you. Oh, they are real actually. So this is 256 gigabytes of flash memory on this one board, and you get 24 of these memory sticks in a dual socket server, and they run at 8800 megatransfers a second. That is what you usually only get in gaming systems, and that in a server is massive bandwidth. With a dual socket Xeon 6900P server, you get 1.7 terabytes a second peak. What I measured in FluidX3D was 1.2 terabytes a second. That is bandwidth that you usually only see on a high-end GPU, but those are limited to like 80 gigabytes. And here you get 6 terabytes of the stuff, which is fantastic. Unfortunately, it isn't so easy. It isn't as easy as it sounds. So going with CPU means I don't need domain decomposition. I can do it just with one gigantic domain. But the first problem that we encounter is that the 32-bit linear index for the grid cells, it overflows if you have more than 4 billion grid cells. And on the GPU side, this wasn't a problem so far, because 4 billion grid cells means 225 gigabyte memory, and there's no such GPU with so much memory, so far at least. So it wasn't a problem in the past. Always using 64-bit U-long data type for the grid cells is bad, because it causes a lot of slowdown on the gaming GPUs. So the solution is a switchable macro data type. Because OpenCL is compiled at runtime, you can switch between 32 and 64-bit data types on the fly. When the setup tells you need more than 4 billion grid cells, it compiles the entire OpenCL code with 64-bit indexing. And then you don't have a limitation on the grid resolution anymore. So that's the benefit of OpenCL being compiled at runtime. Yeah, problem 2, more problems. Some buffers are duplicate for host and device. When I first experimented with the super high resolution, this meant I could get up only about 90 billion grid cells, which was so close to the 100 billion. And then I realized there was a thing called host buffer, zero copy buffers. So the solution is zero copy buffers on CPUs, and also works for integrated GPUs. What this means is that usually when you have part of the memory host, so this is only the observable variables we need in host memory, the density, velocity, the flex. We need copies of that in device memory, but on the CPU, both of those are on the same system host memory. So for this device part, we just can cancel those out using the pointers to the host memory. And this feature is called zero copy buffers in OpenCL. It has 3 requirements. The first one is in the CL buffer creation, you pass this CL when use host pointer flag. The second and less obvious requirement is that the host pointer has to be aligned to 4096 bytes. You can't just use any random pointer to memory. It has to be aligned to the cache line boundary. And the host pointer allocation also needs to be padded to be a multiple of 64 bytes to be passed to the CL buffer constructor. And yeah, the aligning, how to do that is you allocate your big memory buffer, allocate an extra 4095 bytes, and then you just shift the pointer a bit to the right to where the next cache line boundary is, and you still have enough padded memory available. So that reduces the memory footprint to really 55 bytes per grid cell, even on big CPU and iGPU systems. The benefit with the iGPUs is also that there's exciting development there with the Apple M chips because they have very high unified memory capacity. The same thing with Intel Meteor Lake, where you can put in 128 gigabytes, and AMD Strix Halo as well. So there's some big iGPUs around. And the NVIDIA Digits, I think, is also one of them. All right, now when I really thought I was done with that, there is another problem, the danger zone. So before me, no one has ever tried dispatching a single OpenCL kernel with more than 100 billion threads. And when you try this, of course, the first time it doesn't work because there just was not such a use case in the past. I was the first one to even experiment with this. And it turned out for the Intel CPU runtime, this was in a time before we launched Xeon 6 even, the AVX512 vectorization was broken for 64-bit indexing. However, because I work at Intel, I contacted Ben and a few other guys, and we fixed it, and now it works. So yeah, that is the gigantic simulation that I was able to fit on a dual Intel Xeon 6980p server with 2 CPUs, not a single GPU, and 6 terabytes of memory. And I really got over the 100 billion grid cells, which is a gigantic resolution. This is the NASA X-59 plane. Let me start the video. And the grid cells are 3 millimeters in size, and the plane is like 50 meters long. So the resolution is just eye-wateringly tiny. And the detail that you get here in the bonding structures is really fantastic. And that was also part of one of the updates to make the camera move around in a Catmull-ROM spline around the model. So the rendering here is also done in situ because every frame of that, it would fill up the hard drive. The visualization you see here, if I would have stored the velocity field for all of these frames on the hard drive, it would occupy 7.6 petabytes of memory. And that would be very expensive for hard drive space. And it would also blow up the runtime by like 100x because then the bottleneck to the hard drive would slow it down so much. And in situ rendering is the only way to even visualize so much data. And because I wrote the rendering engine in OpenCL itself with direct connection to the raw buffers in the fast GPU memory already, I can just make the GPU simulate a few time steps, then pause, and then render the data to an image, and then send the image to the hard drive. Yeah, usually for that kind of resolution, you would need an entire supercomputer, and I showed that it is possible to do that on a single server. The runtime of this was 1 month. So it's quite long, but bear with me, it is not as bad as it sounds. Because the server has like 1.5 kilowatts of power consumption. So it's very reasonable power consumption. If you would run this on like 100 GPUs, the power consumption would be similar. The runtime would be shorter, but the cost of hardware is gigantic for so many GPUs. And powering one of those Xeon 6 servers is quite easy on the infrastructure. I know it from university with our big GPU servers. They need so much power and so much cooling that we had to move them out between multiple buildings many times because the cooling wasn't sufficient. So this is quite an exciting way to do super large simulations with reasonable hardware cost. Yeah, and to conclude my talk, my message to you is that you all have the power to change the GPU landscape. When I started FluidX3D like 7 years ago, I was just a student at university and no one ever knew me. And I make a difference with the software. I make a difference with OpenCL, and you can do so too. The OpenCL standard itself is not set in stone. We are always working on improvements and further extensions to it. If you have any suggestions, come to us, to the Corners Group OpenCL advisory panel. New hardware also brings many new hardware features, the tensor cores and whatnot. And the OpenCL standard still has a way to go to also support some of those features. But OpenCL today is better than it ever has been in the past. The OpenCL vendor implementations, they still have some bugs. They are not perfect. If you find any of the bugs, report them. The vendors are very eager to fix the bugs. And you would think that NVIDIA is very opposed to OpenCL. They are not. Whenever I report bugs to them, they get back to me within like less than a day, and they are very fast to fix them. And of course, we at Intel and the people at AMD the same way. So OpenCL today is better than it ever has been. And the GPU landscape is made by the people for the people, and you have the power to change it to the better by writing good software, by using other people's software written in OpenCL. And you can make the choice to go with OpenCL or SYCL over proprietary languages. So the power is really with you. Yeah, thank you for your attention, and I'm very happy to take your questions.
I'm just curious, like this NASA airplane, how it like moves through air. At which velocity were you simulating it?
That was at 300 meters per second. So when it does the landing approach. Oh no, 300 kilometers a second. Sorry. So it's a quite slow velocity. Lattice Boltzmann without extensions, unfortunately, can't do the transonic or hypersonic regime where the air really compresses. So this was only at the landing approach where the air is only weakly compressible. The limit for lattice Boltzmann is around Mach number 0.3. Anything below that will work.
But is there actually like a simulation scheme for hypersonic?
Yes, there is simulation methods for that. Usually they use different tools, finite volume method, for example. NASA has a code for that. It's called FUN3D. And they are expensive to run. You don't get nearly as much resolution. There's one simulation NASA did for a re-entry capsule entering the Mars atmosphere at 1 billion grid cells, and they needed 27,000 GPUs for that for a week. It's very expensive. But there is ways to do hypersonic regime.
Nice talk. I have maybe two questions. So what is your multi-node story? So do you have any MPI support, or you more rely on remote GPUs as Poker?
Yeah, I don't have an MPI implementation yet. Some people have asked me for it. And so far for multi-node, I've experimented with Poker Remote a little bit, but I mostly stuck with single node. It makes it easier. It is compatible with more hardware. Not all of the hardware has an MPI implementation. If you choose to go with MPI, you need to make a preprocessor switch, so you can switch off the MPI support in the code entirely, or it won't even compile. And my focus was more on out-of-the-box compatibility with literally every computer. Like you can go in a public library with a 15-year-old computer and FluidX3D will run on it. That is my requirement because I want to make computational fluid dynamics accessible and available to everyone, also the people who don't have an abundance of hardware.
And second question, so you support only one domain size, right? So if you have some heterogeneity, you need to create multiple or stuff like that. When you saw in your example, so you create just stub and you run multiple of them. Okay.
So in theory, it is possible to make the domains for domain decomposition different sizes for heterogeneous architectures, but it is not. There's not too much benefit to it. An example, in a gaming system, in my system at home, I have an Intel B580 Battlemage GPU with 12 gigabytes of fast memory and an integrated GPU. And the discrete GPU is just more than 10 times faster than the integrated GPU, and it doesn't even make sense to pair the two because the slower one is the bottleneck. And even with heterogeneous domain size, there's still some overhead for the communication over PCI Express, and that eliminates any benefits. So for simplicity of implementation, I've stuck with the same domain size for all of the domains. And in some cases, like with the Cessna demo that I've shown, with one A100 GPU with 40 gigabytes, it is like twice the size and twice the bandwidth of all the other GPUs. Then this one fast GPU can just take multiple domains. That also works.
Thank you.
Hey, I was wondering. You are using 16 bits floating point numbers mostly for compression, but how much of a cost or gain do you have in terms of performance when using FP16?
Good question. The thing is with the memory compression, with FP16, I can fit twice as many numbers in the same memory capacity, but I can also load and store twice as many grid cells in the same time. So it makes it almost twice as fast. So I get double the performance from it even. And many other mixed precision codes, they are using FP16 for the arithmetic and not for storage. But here the benefit is really only in the storage. The arithmetic has plenty of extra spare room. The arithmetic intensity of FluidX3D with FP32 is at 2 bytes per flop, at two flops per byte. So for every byte of memory that I load and store, it only does 2 flops. And the hardware arithmetic intensity for an RTX 3090 is like 80 flops per byte. So there's so much room to do extra arithmetic. And it is very much bottlenecked by the memory access. And that's what I was feeling with the FP16C format that is quite costly in the compression and decompression because it is emulated in integer arithmetic. The GPUs have so much spare arithmetic power that they can just handle the extra clock cycles for compression and decompression at no performance hit. And yeah, performance is still doubled because of the memory bandwidth reduction there.
Thanks a lot.
Yeah, you already asked my first question, so I only have the second question for you. Could you even compress it even further if you weren't bound to multiples of 8 for the floating point numbers, like for example, 12-bit floating point number?
Yes,
if you could do
it is a possibility. Unfortunately, I'm bound to multiples of 8 because the OpenCL data type, the smallest data type that you can do reads and writes is char or 8 bits. But there is ways of like calculating multiple grid cells or fusing the numbers of the density distribution functions in like one blob of bytes and then chopping it up into 12, where each part is 12 bits, but then chopping it up into chunks of 8 bits or 16 bits. That is a possibility. I haven't explored it. I've just tested with 8-bit, so like an FP8 format before it was cool. I tried it, and it is insufficient. So at some point, the precision you get is too little. With FP8, you have to keep in mind you can only represent 256 different numbers on the number line. And that is insufficient for the density distribution function. Maybe some block formats would also be viable. That was on my list for a long time to experiment with, but I haven't yet tried it out. So there's still some room for further optimization, but you won't get too much benefit anymore. So we can maybe reduce a couple bytes still, and squeeze even more grid cells in, but at some point you will hit the precision limit.
Okay, thanks.
I have 3 t-shirts for everyone who had a question.
I guess I had a question with the rendering. I don't want the t-shirt. I already have one of your t-shirts. The rendering with the on the fly, do you use any of the interop with the other rendering APIs like OpenCL, GL interop?
Actually, no.
Okay.
That was what I was presenting last time at IWOCL 22, I think it was. So I didn't include it in this talk anymore, but you can watch my old talk on YouTube, how I do the rendering with OpenCL, and it's just purely OpenCL based, because in the end, every hardware that can do math can also render, because an image is just an array of integers, and each integer represents an RGB color, so any hardware can render. But not any hardware supports OpenGL or the rendering APIs. NVIDIA A100, for example, it lacks some like the texture units and some hardware that is required for proper API support. But when I do all of the rendering just in pure OpenCL, it works even on an A100 or any other GPU that even lacks the rendering hardware. I can even do OpenCL ray tracing on these GPUs that don't have any ray tracing hardware in them. And it's even faster than BVH, what I do. it's a variant of ray grid traversal. This is for the free surface simulations. So I made any GPU be able to render regardless of what the hardware underneath is, and there is the benefit of not relying on any other APIs for that.
I was curious, are you using any kind of checkpointing for a months-long run on a 6 terabyte machine?
So you mean every once in a while, like once a day, store a checkpoint and then resume? That is a possibility. So far, there wasn't a need for it. With GPU systems, the simulations, they finish in less than a day. So if the thing crashes somewhere down the line, I can just restart and the cost isn't too great. This one Xeon 6 simulation that ran for a month, it was a bit different, and I started it 1 month before the Supercomputing 24 conference, and I wanted to present it there, so I had one shot at this and it worked. And no checkpoints. I haven't implemented it. It is possible, of course, to do it. The memory requirements are insane, but it's possible.
Bold.
Yeah. But the better thing is to make the software so reliable that it just never crashes. It's actually what I did with FluidX3D. I have a 0 bug policy. There's 0 known bugs currently. I made a big hunt for all of the bugs last year.
Yeah, thanks for the presentation. Super interesting. You've highlighted that your code runs on basically everything that can do arithmetic, but if you could wish for special hardware, would there be anything that you would like in CPUs or GPUs?
I think this was in a time before Alchemist came out, before I joined Intel, and I was on the Intel Discord, and I like photoshopped a picture of the Arc PCB, where like it is completely clustered full of GDDR6 modules. That's what I want. So Yeah, the hardware chips itself, they don't have to be big. If you look at the new NVIDIA Blackwell chips, they have gigantic silicon area, and all of that isn't needed for these kind of HPC simulations because there's so much memory bound. Like you could reduce the chip size to a quarter, and it would still be just as fast. The problem is that they have the memory controllers at the perimeter of the chip, and they the side lengths of the memory controllers, they basically dictate the area that the entire chip has to be. So it's still a bit of a requirement to have huge chips. But if it was just for me and like physically, electronically possible, I want hardware that has gigantic memory capacity, gigantic memory bandwidth. It's very interesting that we see the developments with all of these AI chips because the AI development finally creates a gigantic demand for high memory capacity and high memory bandwidth GPUs. That's what we see with NVIDIA Blackwell and MI300X. And you've seen that they are exceptionally well suited also for HPC because the memory bandwidth is just gigantic there. But it's a very difficult technical problem in the end with the HBM memory stacks. They have to stack it vertically because they can't put it any further away from the chips due to signal integrity. And if you stack too many layers of the chips vertically, then it becomes at some point a problem with cooling because the chips at the bottom, at some point, they will just start to melt.
What they're saying, we should start making chips snowflake shaped instead of square, maximize the edge area.
Yeah, that's what I'm saying. Give me a snowflake chip. I mean, it's a real possibility with the 2.5D manufacturing, a bit similar to what we have at Intel with Meteor Lake and Arrow Lake, where we have a base die and then several top dies on it. You could make it different shapes than a rectangular. More questions? Who wants t-shirts?